You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Server Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Storage failures are one of the most critical problems a server can experience. They range from total volume loss to intermittent issues such as slow read and write speeds or unexpected file corruption. These problems affect user productivity, application stability, and data integrity. The symptoms may first appear in the operating system logs, in application error messages, or through end-user reports of degraded performance. The CompTIA Server Plus certification includes recognizing and resolving common storage-related failures using tools, logs, and configuration analysis. Storage issues are often misdiagnosed because they resemble other system problems. For example, a slow drive may look like a network bottleneck or a processor spike. File corruption might be mistaken for application bugs or permission errors. These problems often develop gradually, showing subtle signs before causing full outages. Technicians must approach these failures by analyzing the full path from the physical storage device up to the file system and application layer. Mount point failures are one of the most visible signs of a storage issue. When a system cannot mount a volume, it may report errors such as device not found, file system not clean, or mount failed. These errors can occur if a drive was physically removed, a partition is damaged, or if the file system entry in the configuration file is incorrect. On Linux systems, use the mount command, list block devices, and review boot logs. On Windows systems, use Disk Management and Event Viewer to confirm the cause. Slow storage access can be difficult to diagnose without proper tools. Aging disks, misaligned sectors, or storage queues that are saturated with requests can all lead to performance issues. In virtual environments, shared storage may also introduce contention. Use tools such as IOstat, IOtop, or vendor dashboards to monitor input and output wait times. Prolonged storage latency causes noticeable application delays and must be investigated at both the file system and disk levels. File corruption typically appears as unreadable files, checksum mismatches, or invalid file headers. These failures are often the result of power loss, improper shutdowns, physical media defects, or firmware bugs. On Linux, use file system check utilities, such as FSCK or Z file system scrub tools. On Windows, use the check disk utility. These tools can detect and sometimes repair low-level corruption to restore access and prevent further loss. System logs provide critical insights into storage problems. Look for recurring input and output errors such as device reset, bad sector, or timeout. Trace these messages back to the affected block device or volume. Pay attention to repeated patterns and devices that consistently generate alerts. These are often early signs of hardware degradation that will lead to failure if not addressed promptly. Drive health should be checked using self-monitoring analysis and reporting technology. Use the Smart Control utility to view reallocated sector counts, temperature data, and cumulative error reports. Track these values over time to detect negative trends. Many failures can be predicted in advance if drive metrics are reviewed consistently. Document threshold values and set alerts when devices approach risk limits. Partition table problems can also interfere with storage access. Misaligned or corrupted partitions may prevent the system from mounting a device correctly. Tools such as fdisk, parted, or gpart can be used to inspect and correct partition layout. Always back up the master boot record or the GUID partition table before making changes. Modifying partition structures without a backup increases the risk of permanent data loss. Storage controller drivers and firmware also play a role in stability. Redundant array controllers, or SAS and SATA interfaces, may have bugs or known compatibility issues. If logs show errors originating at the controller level, update the driver or firmware based on vendor guidance. Controller logs are typically stored separately from the operating system logs, and may require specific tools to access. Failures at the file system level often originate from metadata inconsistencies or journaling errors. These issues reduce reliability even if the hardware is stable. Use native utilities such as XFS Repair, ext4check, or the appropriate file system recovery tool. When diagnosing file system failures, always mount the affected volume in read-only mode to prevent making the problem worse during analysis. Misconfigured mount options can also lead to performance problems or prevent recovery. Options that disable journaling, change write caching, or bypass standard recovery behavior can introduce data risk. Always review the mount configuration in files such as /etc, /file system table, or systemd mount unit definitions. Validate that mount flags match the file system's capabilities and that no unnecessary overrides have been applied. When a system is shut down improperly, the storage may be left in an unclean state. File systems that rely on journaling can usually recover, but only if the journal is intact. Use recovery flags, journal replay tools, or safe boot options to allow the file system to correct itself. Before restarting services, validate the volume to ensure all corruption has been resolved. File checksums can confirm that key data has not been silently altered during the recovery process. In cases where file corruption has already occurred, a verified backup is the most reliable recovery method. Restore the affected files or entire volume from the backup archive. Document which files were lost, which were restored, and how the recovery was validated. After restoration, test file access and monitor for ongoing corruption. Never assume that backup integrity is guaranteed. Each restore must be verified. Prevention is essential to avoid recurring storage failures. Schedule regular file system checks and monitor SMART attributes proactively. Replace drives before they reach their failure thresholds. Ensure systems are always shut down cleanly during maintenance. Power loss and unplanned reboots are leading causes of file system corruption. Installing uninterruptible power supplies can also reduce the risk of abrupt storage failure. Use scripts to test file access during regular system health reviews. These tests should include creating, modifying, reading, and deleting test files. Pay close attention to permission errors, I/O exceptions, and incomplete write operations. Combine these checks with application layer tests to ensure that storage problems are not silently affecting system performance or stability. Support staff must be trained to isolate storage faults accurately. Teach them to separate operating system issues from file system problems and from block-level hardware faults. Provide visual triage charts that explain how to identify each failure type. Include examples from real incidents. Add storage fault isolation exercises to response drills to build team competence before an actual outage occurs. When a storage failure is resolved, log the details in a centralized record. Include the symptoms, the diagnostic tools used, the files or volumes affected, and each step taken to correct the issue. Also log the mount configuration, device identifier, and operating system version. Archiving this data supports audits, facilitates knowledge transfer, and improves incident response for future events. Track storage metrics over time to detect degradation. Use monitoring platforms such as Prometheus, Zabbix, or vendor-specific dashboards to collect performance data. Watch for patterns such as reduced input and output operations per second, increased latency, or growing bad sector counts. Set alerts to notify administrators when performance deviates from baseline. Early warning is the key to proactive maintenance. In conclusion, storage failures can be catastrophic, but they are also preventable and diagnosable when logs, metrics, and recovery processes are used effectively. Mount errors, slow access, and file corruption all stem from underlying causes that can be tracked and resolved through structured analysis. A server's data is only as reliable as its underlying storage, and careful monitoring is the only way to ensure that reliability. The next episode focuses on adapter-level issues, including host bus adapter failures and storage controller problems. These middle-layer components are often the hidden cause of persistent disk access problems. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.